This is what motivated us to start this line of work. In fact, it's the motivation for many other work we do, is that our ultimate goal for scientific computing is to make system prediction and analysis for very complex systems, for very practical. The problem that, in my mind, we have more or less reached the so-called point of diminishing return. You can keep adding physics, keep adding equation to a model, and your model become more and more complex, take more and more time consuming. It doesn't necessarily mean your model is much better. As we are coming from data, just all the way, get a piece of computer model as the eventual things to help us analyze and understand the physics. So that's our whole point. It's always been data-driven. Before that, let me give you a basic setup. In all this talk, I will give you all kinds of numeric examples. In all the examples, we will sometimes have the true system in the background. All right, so that we know that the only way this is useful is that this will be used to generate the training data and then to validate. So knowing this true model in the background in no way whatsoever to help us the method. It's just the way to validate things. The method I will discuss is so-called flow map learning method, and just have the name, everything. All right, so let's see why this works. We'll start with a simple system. All right? Suppose I have an autonomous dynamic system, vector system. It's autonomous, there's no T here. And suppose I do not know what F is. I don't know the equation at all. So, but what we do have are the measurement of X, like we said before. We have a measurement of X, the entire state variable of some trajectory, we have that. Right? So the reason this is called flow map learning that we are not, there has been quite some work to try to use data to recover the right-hand side, called equation recovery, and with some polynomial sparse recovery, and even some neural net, we don't try to recover equation. My underlying reason is that even if you recover the equation, so what? You still have to discretize it, try to solve it. So at the end of the day, having equation doesn't help much. As I said, the right-hand side eventually is a piece of code. So let's just go that directly. So we try to find the flow map. What is flow map? It's a very simple thing. Flow map just said, knowing equation, it's a map between the solution at two states. Right? So if I have a solution at t0, may not be zero, it's time, and I have solution at t, the mapping is just this map solution from t0 to t, in this case. For autonomous system, time doesn't matter, only the time difference matters. So whatever time difference between these two, that's the map. And this map is a simple one because this map is nothing but of the same dimension RD to RD. If my state variable is D dimension, it maps whatever at the D dimension to next another D dimension. And here we are going to, from our measurement data, I'm going to take the neighbors. They're separated by a very small time step, whatever the measurement dictates, called it delta or delta T in numeric analysis. And since time doesn't matter, I'm only looking at time difference. I'm going to look at my measurement two solution at two time level consecutive to each other, right? I'm going to call this one x0, the other one x delta t later. And this flow map says this is the flow map parameterized by this delta t. I can pull a lot of this from my measurement because time doesn't matter. I can treat every pair as starting with some initial condition and evolve by an unknown equation for one step. We have data here, we have data here, and that's all we need. And let's use neural net to map something in between. So all we are trying to do is try to find a function map of RD to RD. So let's make this more interesting because if I observe everything, it doesn't really do much. Like I said, in most example problems, we are not be able to observe everything. So again, let's say I have a dynamic system. I don't know the equation to start with. That's difficult. Make it more interesting, more difficult is that in this X, I can only observe a Z, the subset of it. Or whatever D can be 1, 2 in some high dimensional space. The rest variables, I have no data. In fact, you probably have no idea they even exist conceptually because all you know, I see this, that's all you see. All right, so this is what I have, trajectory data. I'm trying to, so we ask questions. So can we create a model for this? With understand, I don't even know the closed system in the first place, but I just want to do that. All right, so turns out this can be done, mathematically speaking. There's so-called well-known, so-called Morris-Zwanzig formula says exactly that. Having this autonomous system for subset variable, there exists equation for the subset variable sort of self-close by itself. Right? So this would be the memory. If you do neural net, it would be the structure. So I need data for the current step, one step back, two step back. This would be example that your memory only requires you 3 terms. Until your memory is not very long, you just need 2 extra terms here. But it will map the future. You have enough data. I'm going to feed this in here. I'm going to feed the next one as when I compute the error exactly like I did in the incident example. And this is the basic of that work. Let's make this slightly more interesting. In fact, a nonlinear example would be some kind of slow, fast, very chaotic system. The true system, again, the true system is what we use to generate data, is this, has 3 slow variables, 1 fast variable, depending on epsilon. Right? Mathematically speaking, if I take epsilon to 0, you can do homogenization. The slow variable would follow this, right? So let's assume we're not able to measure the fast variable. They go too fast. It's very hard to measure them. Let's just say I can measure the 3 slow variables with data, and I want to create a model for the slow variables only. Again, they do not close by themselves. It depends on y. In the limit, there's a closed system for of epsilon go to 0. It's closed by itself. But when epsilon is 0.1, the slow variable cannot close by that. But we observe x1 to 3 of memory length 1.2. Again, very short. We train a network for a model for x1 to 3, not knowing anything about y. And this is the model prediction of up to 400. I didn't even plot the first 200. It's 200 to 400 because I put in the same plot. Everything looks random. In fact, it's not. This is a deterministic chaotic system. You can see it's not random. Error evolution of all 3 variables in L2 of the neural network model up to 400. Again, you only observe 1.2. And you can go to 400. The error is here. And this is this model. This is the typical model error behavior we see for dynamic system or any approximation method will have error grow over time. So I want to speak just for a moment about PD because obviously this all works well. What about PD? Just a few moments, right? So PD, let's just say I have a PD, but I don't know what it is. But what do we do is that I observe my solution at a set grid that we always do. So suppose you have finite difference, you observe your solution at these grid points as a snapshot at different time. I'm going to write. So every observation on grid points is just one big vector. If you have 1,000 grid points, this will be a vector of length 1,000. Right? It's just one big vector, and I have this observation over different time. That's my trajectory. It's exactly the same setting as a dynamic system. So nothing is missing. If I'm observing all my u's here, no missing variables. Oh, I just need map one-step mapping. I don't even need a memory. Let's do that. So it's autonomous. Time doesn't matter. So put this current as input, put this as output, connect a network in between should work. It's just a dynamic system. The simplest case, the flow map learning I discussed, except it doesn't work. So this is our network structure. This is the nonlinear scheme I have. So I'm going to create a network structure, giving the input VKN, a big vector. We should have physical structure. I'm going to put a network here, this to represent F1. And put another network in parallel to represent F2. And then the next one to represent Fj. I don't know how many J's, but I'm going to put a few there. Then I'm put a network here, cut across it, operating component-wise on everything to represent this, which is L operating in my PD. Putting all these things here, I'm going to map this back to with a +1 here, this delta T +1 here. My output would be here. Now, if I have enough input-output map, which I do, I can train a network like this, as opposed to connect them with a simple, fully connected network or do a simple convolution if that convolution doesn't matter. Well, in fact, this is almost like convolution. The convolution is almost like this without this layer. This is a critical layer. If you don't have this, you will not be able to enforce continuity here. That's what we observe over and over again. When you don't have good continuity, regularity, eventual stability kills you. This will be the interesting example, tough one, the Burke's equation, right? So I will observe one step of solution evolution. How did we generate the training data? We do some random sine cosine function. I mean, arbitrary with number, so it's very smooth. We solve this smooth function by one step. It is still smooth, one delta t, no shocks whatsoever. But you observe any of this, give a new initial condition, let the model evolve by itself over longer time, it will find the shock at the right time. In fact, quite accurately. So this is something I would like to say. This method, you don't need to see the physics to predict the physics. In your training data, you don't need to see what you want to see. In fact, my instant example would be the same thing. You never see in your training data, never have bifurcation, steady state, but it will develop, it will get there. If you do very short-sighted one step correctly, it will get to the correct physics. Just make it complicated. I can say, oh, what if I don't observe the entire domain? I only observe 40% of the grid points evolution. I trim them. This would be long vector. I only observe partial of it, and we need memory. The network gets the structure earlier and also involve memory. You can still do prediction. This is not as good as before, but 40% of domain shock evolution, I think is reasonably good.